Welcome, everyone. We start, finally. So I'm really happy that you are all joining for the final presentations of this year's BL4S winning teams, either live here or even connected via video. Thank you very much already. The teams are very nervous now, but I'm sure they do a great job, as they did in the last 2 weeks. So we had 2 very exciting weeks with a very full program. And although they worked already from 9 in the morning to 8 in the evening, they decided finally to have some further night shifts in order to take more data. So we are very curious now about their preliminary results. And I would like to ask DESY Chain to start with your final presentation.
Are we using the microphone? Yes.
Okay. Is it? We good? Okay, so hi, we're DESY Chain, and before we get started, we just want to throw out a big thank you to Paul, Christobal, Marcus, and Sarah for making this whole adventure possible, and your endless patience with putting up with us. So, I'm Sophie.
I'm August.
I'm Melody.
I'm Sam.
I'm Ariana.
My name is Derek. I'm Lem.
And I'm Charlie.
Okay. So for those of you who don't know us yet, I'm going to talk a little bit about where we're from. We're from the state of Utah in the United States. Utah's a pretty outdoorsy state. We've got 5 different national parks that are known for their red rock. It's a picture in the corner. And we claim to have the greatest snow on Earth, so if you ever want to get some good skiing, that's where you go. Most of us attend West High School, which is in Salt Lake, the state capital. And a lot of us either are in the International Baccalaureate program or graduated from it.
So as you can see, there's also some college logos up there. So evidently we're not all in high school anymore. So actually Lam and myself graduated this past spring in the class of 2019. So we're both college students, and I'm at Haverford College. I've moved across the country to Philadelphia, Pennsylvania to study physics. And Lam...
And so I'm still going to school in Utah at the University of Utah, and I am studying pure mathematics.
So, obviously this was an amazing opportunity for us to be here, and so we chose to extend that opportunity a little further by going to CERN with lots of pictures. So we got, since the long shutdown was happening at the Beam, which is why we're here at DESY and not at CERN, we actually got to visit some of the detectors and experiments that would otherwise be inaccessible because there's a lot of radiation passing through them. So we got the chance to visit CMS. Shout out to Sasha for showing us the data collection, the data center, those pictures up there, although of course he generally has more important things to be doing. And then at DESY, we also got to see a lot of the cool experiments that are going on here. We visited the Hera, the Petra 3, the European XFEL, and got to see all the pretty spectacular things they're doing at those experiments.
All right, so let's cut to the actual science. Okay, so the aim of our proposal is to study the relationship between scintillator thickness and energy deposition. So the original proposal that we submitted to the program started with us selecting either electrons or positrons, sending it through the scintillator, and seeing the luminosity produced there. No, I don't. Sorry. Then it would go through the halo counter, which would stop extra deflections, and finally pass through the big red magnet, which would bend different particles at different angles. So then we would reconstruct the particle path through the DWCs and use that theta to figure out the energy loss of the particle. The calorimeter is just a backup for energy loss.
A little bit about scintillators. So scintillators are materials. When you hit them with energized
particles, they basically fluoresce. So this happens because of things called fluors. Fluors exist in the matrix of organic scintillators, and basically when you energize them, hit them with a whole bunch of energy, they jump up to different energy levels, and when they fall back down, they emit these lights. And this light we can actually measure using photomultiplier tubes. And get on to
So basically, we're looking into the potential, or we were looking into the potential for nonlinear behavior in scintillator outputs, which can be characterized by this thing called Burke's law, the equation up there. Basically, what it says is that at high enough ionization densities, rather than luminosity increasing like proportionally to energy, it gets quenched through a variety of processes. So you can kind of see that in visual in the graph in the corner. Without Burke's law, you can assume that there's like a completely linear correlation, but with Burke's law, you can kind of see it slowing down as it increases and reaches the point of saturation. Anyways, so I'm not going to read all of these, but these are some questions that we kind of considered in the making of our experiment and throughout the process. So one question was, does this model work well in our circumstances with the energy levels and the scintillators we were using? Some models also had like other factors that played into it, so we had to think about that a lot. And then also just like other factors that may have an impact on it, like annihilation of positrons, which we wouldn't think would make it a difference, or yeah, just all to look at the efficiency of scintillators.
So after emailing our support scientists, we actually had to change our setup so our experiment was actually feasible. So we added in the trigger scintillators to provide a trigger, and then we added in the mimosas before the magnet just for tracking. And we also replaced a lot of our delay wire chambers with micromegas because they have a larger area and thus can detect more particles. It was unnecessary.
So for data collection, we basically measured the luminescence of the scintillators using the photomultiplier tubes, like I mentioned before. And from this, we can basically plot different graphs where we can observe how luminescence is affected by scintillator thickness, how much energy is deposited in the scintillator, and yeah.
Okay, so here are some nice visual aids for scintillators. So basically, what we tested was different gigaelectron volts of our particle beam of both electrons and positrons, but we wanted to change a few more variables than this. So we ended up changing the thickness of our primary organic scintillator, as well as trying a secondary organic scintillator and a crystal scintillator to measure the differences in our dampening effects between different materials and thicknesses.
All right, so of course this is experimental science. Nothing ever goes right. So we ran into quite a few problems during the run. So one of the big ones was an issue with the micromegas detector, the first one we had in our setup. So these were actually on loan from CERN, and the first one picked up some moisture while it was traveling, we think. And so when we ran the high voltage to it, it started sparking, which is generally not a good thing if you want good data. So we took it out to fix it, replaced it with a temporary delay wire chamber, which worked fine for data collection, except it meant we couldn't run the magnet at high enough current, since then the beam would actually bend outside the range of the detector. So to fix it, we baked the micromegas, or Marcus did at least, to remove the moisture, and then we tested it to see if the issues were fixed, if it was actually giving us good data, and it was. So we flushed it with the argon CO2 mixture that the detectors use to replace the air that had gotten in during the baking and the testing, and then re-added it to our experimental setup so that we could actually get data where the beam was within the range of the detector and not nearing the edge at high magnet currents.
Okay, so possibly the largest issue that we faced were actually the time constraints with the 2-week time period. So basically we had to iterate through many different parameters because not only did we want to test for scintillator thickness, we also wanted to test for different scintillator types and different energies and different amps for the big red magnet. So we had to iterate through all of these different possibilities with a limited time period. So obviously we fixed this issue with night shifts. But other than that, we had to decide which data we wanted to prioritize for later analysis. So we actually didn't end up running all of the different amps for the big red magnet for all of the different energies. So now we have a more limited but possibly better data set. Oh, it's Charlie.
Yes, me again. Another detector issue. Our calorimeters were experiencing light leaks, which is also not a good thing because it means that light from outside is influencing the light we actually want to receive from the calorimeters and causing a lot of erroneous data that we were getting. So we fixed it with a lot of tape. Essentially, we wrapped it in black tape to stop any light getting in. It took some of the already limited time we had, but it was the best way to ensure that we actually got good data from these detectors.
Now we're going on to basically our results so far. We only finished taking data yesterday, so we haven't had a ton of time to come to conclusions, but we have started working on it. So basically, overall goal of data analysis, I mentioned this a little bit earlier, but I want to make it very clear. We want to figure out the relationship between luminosity and energy loss for different thicknesses of scintillators so that we can gauge their effectiveness. And the idea is to find a model using Burke's law to fit it for these scintillators.
Before we actually can do any data analysis, we actually have to convert all of our data into, we basically have to process our raw data into what we call cluster data. So basically, from our raw data, a particle can actually trigger multiple pixels or strips in the sensor. This leads to a group of different triggers, but we want to group all of these triggered sensors into one particle for data analysis. And so I actually wrote my own clustering algorithm. It was based off of DBS scan. For anyone that knows that, basically it looks at a pixel. It looks at a point, and it has two different parameters. One is min sample and one is EPS. Basically, min sample counts how many points are inside the radius of the EPS. And this is basically what I really do. I find the distance between two different points, and if they are less than or equal to 1 unit away from each other, I put them in a group called a neighborhood, and I basically iterate through all these points, and so I can get all the neighborhoods, and then from each individual neighborhood, I can calculate the mean, and then call that one particle. And next slide, we have a picture of my very long and probably very inefficient code, but that's just how computer science works.
Okay. Another thing we looked at was with our silicon pixel and strip detectors, there's always some noisy pixels which don't react based on particles passing through, but just keep firing. So we did do a little bit of work beforehand. I know there's some reconstructed data that may or may not already have this taken out. We did some work on our end just to look at what the noisy pixels are. On the bottom, you see a graph from our first Mimosa, which is a pixel detector, just to see noisy pixels over a set of runs. And then just some fun number facts. 70% of noisy pixels in any individual run are noisy pixels in 70% of the runs, and 70% of noisy pixels in an individual run are noisy pixels in all the runs. So it just kind of speaks to there's some pixels that are just no good, and then there's some pixels which just statistically are noisy in any given run.
Okay, cool. So now into a little bit more depth of analysis. These are some graphs from one of our micro-mega detectors after deflection. So the big red magnet of the test beam was on for this particular run. So there are two interesting features in this graph that I'd like to point out to you. So there's the peak at 0, and then also the peak around -5. So the peak at 0 is because of non-charged particles that are created in the interactions of the scintillator, which then travel through and create a particle shower when they hit the micro-mega, which causes charged particles, which gives you this spike, even though you don't have particles there, which is also something you have to correct for. There's another level of complexity, but anyway. And then more important to the actual data and analysis that we're completing is this left-hand spike, which is zoomed in on over there. And what you might notice is it's not an even histogram. It lilts off to one side. And so this speaks to how there's not even interactions of all particles in the scintillator, and that on one side, some particles will lose more energy and have a higher deflection than the predicted just like single point model.
All right, so when we graph the data for the calorimeters and the scintillators, we can start analyzing the statistical distributions that they both exhibit. So looking at the calorimeter data, the calorimeter histogram, we can see that it approximately fits a Gaussian distribution, while for the scintillator data, it fits a Loudon distribution. And so using the MPV, i.e. the peak of these distributions, we can then using the scintillator plot at least, we can use the MPVs to graph at the various GeVs, which are 1, 3, and 5 GeVs, we can graph the scintillator output, whatever units they may be, at least two different thicknesses. We had a couple other thicknesses, but this is all very preliminary. So at the 1 centimeter scintillator, we see this very kind of nonlinear plot. It's only 3 points, but we'll look deeper into that. But for the 0.5 centimeter scintillator, at least, we see a more linear plot. So then as we go deeper into analysis, we'll start to learn what these really mean.
Anyways, one thing we had to do to make sure that we were measuring our data correctly was to characterize the calorimeters. So what we did to do that is we ran the beam at different energies without the scintillator in the beam and without the magnet, so that we could see what the output that correlated with that energy was. So you can see on this graph, it's like at 3 GeVs and 5 GeVs, and the idea is that if we can kind of draw a line through those and find the correlation, we can, when we get the readouts for our actual data, associate those with different energies so that we can measure the energy at the end, because that's the goal.
Here's a set of very exciting graphs. And each row is any given run, and each column represents a different calorimeter, and the spatial distribution of the graphs on the board is equivalent to how they were set up in the beam. So like it's calorimeter 0, 1, 2, 3, 4. It's the same way there. And these, what's the main thing that's interesting to see from these is kind of to be like, look, with the magnet and everything, the beam is bending and it's hitting different calorimeters. So like, yes, the principle of your experiment sort of works. For example, the first one, way at the top, that's an alignment run where we're just hitting that second calorimeter, and you can see there's only data points in the second calorimeter. Yay. In the second run displayed, the magnet was bent, so it hits both the third and the fourth calorimeters. And that's just interesting to see. And for fun, we can make them into squares, where the color from yellow being the most hits to purple being the least hits is actually equivalent to this graph. So for example, we call the first one, second calorimeter hit most, bam. So again, this isn't actually, it doesn't yet go to how does luminosity of the scintillators is affected by energy deposition, but it does say your magnet's bending, it's bending and it's hitting multiple calorimeters. The particles are bending, they're hitting multiple calorimeters, but they're bending the way that we expect them to, and there's not any big surprises there, so that's just nice to see.
All right, so we have this very color-coded graph. It represents 3 different runs at 1, 3, and 5 GeVs, and you can see 3 distinct clusters denoting that difference. So on the x-axis, we have the sum of the energy of the energy deposited into all 5 calorimeters, and on the y-axis, we have the scintillator output as given to us by the photomultiplier tube. So since this is the energy deposited into the calorimeters, we see that the groups are near their respective energies, but a little bit less, somewhat denoting the energy loss as it went through the beam. And so this is basically the same plot. The last plot was given at 0.5 centimeters. Here we have it at 0.5 and 1 centimeter scintillators. This just also depicts the error bars at each point, and which are the standard deviations. So using naive statistical analysis methods, we might think there isn't a statistical significant difference, but this is all very preliminary. We haven't chosen the best data to represent on this graph, but this is what we have right now.
So now kind of back to us as people and what we've taken away from our experiment. So it was obviously an amazing opportunity to be working here at DESY for the past 2 weeks. We've learned a lot. We all know how particle physics works on a practical level and even just a better theoretical level. So much more than when we came in. Everything was all very loose and hypothetical, I think, before actually seeing the beam. So that was very cool. And because of this experience, most of us are considering careers in STEM and even careers in physics, computer science, or engineering, for the majority of us at least. And so we're all either going to be continuing or starting college with that in mind anyway. And then to sum up what we're going to do with the data that we've collected, obviously we're going to continue analyzing it. We're going to have some more significant results that have a more direct answer to our actual research question. And we plan to try and publish a paper with the help of the lovely scientists here sometime in the next 2 years. So, any questions?
Great, thank you so much. I'm sure there are some questions. Now is your chance before they have to leave tomorrow, unfortunately. Starting in the back. I'm coming.
Hi, nice talk, nice presentation. I have a comment and a question. So on one slide you had the big tag problems, right? So just FYI, in science communication there are never problems, there are only issues. And you fix them, or at least proposed how to fix them. Okay. On your last slide, where you showed the result, the energy dependence, potential energy dependence of the scintillator response. Do you expect a dependence of the scintillator response to the particle energy?
I mean, yes, loosely. We expect the luminescence of the scintillator to be related to the energy of the particle, but that passes through, as described by Burke's law, which we're characterizing it by, if we're looking all the way back there, or if no, we're going back to questions. So we expect that. Currently, we don't have that, but we'll continue to refine what we're looking at, and hopefully get some results that better match the theory and experiments that have already been done in this field. All right.
Thank you.
Any other questions? Maybe also from the connected people, our colleagues outside of DESY.
We're here all night, folks.
Yeah, you always have to give them like a few seconds in order to connect with their microphone. Last chance. Okay, then thank you again very much. Okay, then it's time for the second team, the particle peers from the Netherlands, to say something about their 2 weeks experience here and hopefully some preliminary results as well.
Okay,
So we are the particle pairs. Okay. And I'm Frédéric, that's Yannick, that's Isabelle, Ilja, Abrasha, and Cecile. And this is a picture of us with the mayor of Groningen. We're from the city of Groningen, which is in the north of the Netherlands. This is our two school buildings. And so we live not that far away from Hamburg. Okay. Well, we're going to tell you something about what we did the last 2 weeks. And therefore, we need to explain something about the theory behind our experiment and what our experiment is about, and how we analyzed, how we started analyzing our data, and how we are going to continue analyzing our data.
Yes, so first let's dive a bit into the theory behind our experiment. As our theoretical framework, we use the standard model of elementary particles. And one of the main concepts is the electromagnetic particle shower. Can we go back? Thanks. In the shower, there are 3 types of particles. As you see, electrons and their anti-particle positrons, and the gamma rays. So important to note is that electrons and particles are antimatter and therefore have lots